This is Unit 3, Video 4. In this portion of the notes, Part B, we will talk about light and electrons. Specifically, we'll be focusing on electrons eventually because that's what concerns us. But as we'll see, light will allow us to understand electrons. So the question we'll begin with is, what is light? In order for us to understand, again, what electrons are doing, we have to understand light at first. Now, light is a very strange substance. Scientists still don't have a full understanding of what light is. We know that it has a strange nature to it, but we still study it, and we find new and new ideas as we try to understand light. But light will be the key to us understanding electrons. We must first understand light. So let's dive in. Light behaves as both a wave and a particle. It's got what's called a dual nature. So particles are little tiny pieces, little tiny parts. Atoms, for example, would be an example of a particle. And there are experiments in which we see light as a particle. But light can also be thought of as a wave. A wave is actually a form of energy. This is energy. And so we'll take a look at light as waves and light as particles in this lesson. So light as a wave. A wave, like any wave, think of an ocean wave or a sound wave, has two characteristics, or a few characteristics. The first one is wavelength. The wavelength is actually the distance between waves in meters. So the distance between the top of one wave, called a crest, and the top of another wave, called a crest. You can actually measure this. So if you take a ruler out and actually measure it, say from here to here, say this is 25 centimeters. That would be the wavelength of this light, 25 centimeters. And there is a real light wave that has this wavelength. The other feature of light is its frequency. The frequency is the number of waves that pass a point in 1 second. So if you take a look at the top wave, we can actually calculate its frequency. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we can say this has a frequency of 12. Now the unit for this would be Hertz. Hertz, or you can say waves per second. So you can either say per second, or you can say 12 Hertz. The bottom wave, notice, has 1, 2, 3, 4, 5, a frequency of 5 Hertz. So you see both a wavelength and you see a frequency. Now the two are inversely related, which means as frequency increases, the wavelength will decrease. You can see this in the example. The top wave has a very high frequency, but it has a very short wavelength. In fact, if you take the distance between here is small. Whereas the bottom wave has a low frequency, but a high wavelength, or a large wavelength. So these are called inversely related, which means as the wavelength decreases, the frequency increases, and vice versa. That's an inverse relationship in science. Now, if you take light and pass light through a prism, a very interesting thing happens. This has actually been done quite a while ago by Isaac Newton, and he realized, or he saw, that light being passed through a prism comes out in the colors of the rainbow. And this was our first insight into the fact that white light is composed of individual sections, individual regions. And so this is called refraction. Light becomes refracted, technically bent and separated into colors. A similar thing happens if you take a compact disc. You may not know what a CD is, but ask a parent. You'll see the same thing happen. You actually see the colors of the rainbow come out. This is called diffraction or diffraction, which is a similar effect. Both of them actually split light up into its colors, which tells us that light is composed of these different sections. Now we're going to take light, all the possible light out there, and show you the different sections of it. The portion that we can see is called the visible spectrum, which is actually a small slither, small portion of all the light that's out there. The rest of the light we cannot see. For example, we cannot see IR, which is infrared light. We cannot see microwaves, even though we use them. And we cannot see radio waves. And the radio waves actually has a very, very large region, and a lot of these are used to communicate with cell phones. So cell phones communicate with each other and with the tower using radio waves, radio frequencies. So these are invisible to us. However, we can detect them, and we have special devices to be able to detect them. On the other side, we have UV, ultraviolet, X-rays, and then this is gamma rays. This is very high energy. So this is dangerous light on this side. This site is low energy. That's why we use it. That's why we have devices in our pockets that can send radio waves. Now, at the end, at the red end, you see here, we have a lower frequency. And notice we have 700 for the wavelength. This is the wavelength. And at the blue end, we have a higher frequency, and notice a smaller wavelength. So we see that inverse relationship. Now, the portion that we can see is the red to the blue, and usually it's subdivided into 7 regions. So you know about Roy G. Biv, hopefully you know about Roy G. Biv. Red, orange, yellow, green, blue, and then indigo, violet. So make sure you know your colors of the rainbow, and these are the regions that we can see. The rest of it is invisible to us. We'll have to use some machines, special instruments to see the rest. Alright, so how about a quick little question before we go on? Using the electromagnetic spectrum, list these colors in order of increasing wavelength. Now, the numbers are actually right down here for us. So 400 is blue, 700 is red. These numbers, by the way, are nanometers. These are nanometers. Pretty tiny, 1/1000th of a meter. So I want us to list these in order of increasing wavelength. So I know that red is the highest, blue is the lowest. So we'll say blue is first, and then red would be last, number 4. And then between them, looks like we have blue, and then goes green, and then goes yellow. So we'll do green is the second, yellow is the third. So these are in increasing wavelength. So blue has the shortest wavelength. It also has the highest energy. Do the same thing, take a moment, and do the same thing with the other part of the spectrum. Now we'll talk about light as a particle. We've talked about light as a wave. Now think of light as a little tiny particle coming at you. Now this particle is called a photon. It sounds like a proton, but photo means light, so that's why we use the word photon. Now light, remember, is energy and not matter, even though we're thinking of light as a particle here. So a particle of light, a visible light, has about this much energy, 4 times 10 to the negative 19th. Really small amount of energy. And the units for energy is actually joules. It's a unit that we'll use for energy. You can use big J when you're symbolizing energy at the back of it. So light definitely has energy. The energy of a photon is based on its frequency. So here it says, as frequency increases, the energy also increases. So you have more energy for a higher frequency. These are directly related. So a little photon of light coming from here will be a lower energy versus the light that comes out here. In fact, if I were to use color, the top light would actually be red, because red has a lower frequency, and the bottom light would be blue, because blue has a higher frequency. So if you were to see this light, you'd actually see the top light be red, the bottom light blue, because the higher the frequency, the more energy you have. So if you take a look, the frequency, we said that frequency increased going this way, so frequency actually increases to the left, because gamma rays and X-rays have more energy or higher frequency than infrared light, and the energy increases in the same direction. So the higher the frequency, the higher the energy of light. Alright, that actually completes for us this lesson. We'll talk about Bohr's atomic model in lesson 5.